Now start open mapping theorem. Okay. Open mapping theorem. Let xy be Banach space and t x to y be a surjective bounded linear operator. Then T is an open mapping. Okay. How we prove it? We prove now. Let G be an open set. Let G be an open set in X. Then we have to show that. Then we have to show that TG is open. That is, for each y belongs to TG, there exists lambda greater than 0, b lambda y subset of TG. For this we let y belongs to TG. Then there exists x belongs to G such that Tx equal to y. Since x belongs to G and G is open, then there exists a row greater than 0 such that B row X is subset of G. Hence, T of P row X is subset of TG. This marked as 1. Okay. Now we're going to further discussion about that. Note that y plus p1 y0 equal to p1 1 y. By above lemma, there exists r greater than 0 such that BRY0 subset of TP1 X0. Okay. Now this implies that y plus BRY0 subset of y plus TP1 X0. This implies that y plus BRY0 subset of Tx plus T of P1 X0. Okay. Now we erase this our portion. This implies that PRYY subset of T of P1 is X. Okay. Now this implies that rho PRYY subset of row of tv1xx where row greater than 0. This implies that row PRYY subset of T of row B1XX. This implies that P of row RYY subset of T B row XX. This one marked as 2. Hence from 1 and 2 we get B row RYY subset of T B row XX. Okay, then this one subset of TZ. So B delta YY subset of TZ where delta equal to rho R. This implies that Y is an interior point of TZ. Since Y is arbitrary, hence each point of TZ is an interior point. Since Y is arbitrary, hence each point of TZ is an interior point. Hence TZ is an open set. Hence TG is an open set. Now we're going to further discussions about some corollary of this theorem. Okay, we reach this portion. We prove that TG is open and we prove the open mapping theorem. Now we discuss about corollary of open mapping theorem. Let's write this statement of this corollary. This corollary tells us that let xy be Banach spaces. Let xy be Banach spaces. Let tx to y be a surjective, not surjective, this one is bijective. This one is bijective bounded linear operator. Bijective bounded linear operator, then T inverse is continuous. Okay, this one is the Banach bounded inverse theorem. This is the Banach bounded inverse theorem. That means here not surjective, here bijective bounded linear operator. Then T inverse is continuous. Okay. Now since T is 1 1 and 1 2, that means since T T bijective, then T inverse exists. Then T inverse exists. And T inverse linear. And also T inverse linear. Then we have to show that T inverse is continuous. We have to show that T inverse is continuous. Note that Tg equal to T inverse of whole inverse G is open by open mapping theorem. Is open by open mapping theorem. Hence T inverse is continuous. Hence T inverse is continuous. Okay. G is open and Tg is open, hence T inverse is continuous. Now we're going to give one example of where T is invertible but T inverse is not bounded. That means the space is not complete. Okay, we're going to the one example C00 post infinity. We write this example of let C is 00 norm infinity be a normed space, and define T C00 by T of x1 x2 xn 00 equal to x1 x2 y2 x3 y3 xn yn 00 Then we know about that T is linear. In previous class we discussed about that, and also T is bounded. How T is linear? T is linear because T of alpha x beta y equal to T of alpha x1 x2 xn 00 plus beta y1 y2 yn 00. Okay, then this equal to this of alpha x1 plus beta y1 plus sorry, this one not right here. Here we write just alpha T of x1 x2 xn 00 plus beta T of y1 y2 yn 00. This one equal to alpha tx plus beta ty. Hence T is linear. Now T is bounded. How we prove it? We proved it. Norm of Tx infinity equal to supremum of norm of x1, norm of x2 y2, norm of x3 y3 norm of xn yn less than equal to supremum of x1 x2 x3 xn less than equal to norm of x infinity. Okay, so we show that norm of Tx infinity less than equal to norm of x infinity, hence norm of t less than equal to 1, so t is bounded. So t is bounded. Okay, this one is 2, this one 1. Now we're going to this proof of next portions. We erase all the portion. Now here we write 3rd option t is 1 1, and 4th option t is invertible. T is invertible. Okay, third one t is 1 1. How we see that? We see that in this way t x equal to 0 implies that t of x1 x2 xn 0 0 equal to 0, means 0 0 This implies that x1 x2 y2 xn yn 0 0 equal to 0 0 This implies xi equal to 0 for all I 1 1 n. Then this implies that x equal to 0. So this one is t is 1 1, and this implies that t is invertible also. This implies that t is 1 1 and on 2 1 1. So not on 2 needed here. So t is invertible. Okay. Now we're going to further discussion about that T inverse is not bounded. Okay, so we write this. We now discuss about that T inverse is not bounded. T inverse is not bounded. T is invertible implies that T inverse exists. Okay, now T inverse T of x1 x2 xn 0 0 implies that x1 x2 y2 x3 y3 xn yn 0 0. This implies that T inverse y1 y2 yn 0 0 equal to y1 2 y2 3 y3 n yn 0 0. Okay, then we now write here yn norm equal to 1. If we consider y equal to or yn equal to 1 1 1 0 0. Okay, this one n term. Then t inverse of yn non-infinity equal to how much? Supremum of 1 2 3 n equal to n tending to plus infinity as n tending to infinity. So T inverse is not bounded. So the space is not complete. Okay, now we discuss about that one problem which is not complete. Why this one is not complete? Because C00 is not Banach space, not Banach space. Okay, so T inverse is not bounded since the space is not Banach. Okay, so T inverse is not bounded. Yeah, because now we discuss about this open mapping theorem and also bounded Banach bounded inverse theorem or Banach isomorphism theorem. That means T inverse is continuous if T is bijective bounded linear operator. And then also we discuss as one problem. This problem is shows that T is linear, T is bounded, T is 1 T inverse exists, but T inverse is not bounded since the space is not complete or the space is not Banach space. So today we stop here.